Hey guys, Mr. J here. Today we are going to talk about precipitation reactions. This sounds like a new type of reaction, but it's actually not. We've actually already talked about it. We talked about our types of reactions earlier in the year, so it's nothing really new. We're going to actually make it a little simpler than we had previous done it when we did reaction types, and we're going to talk about a new way that we can write some reactions to give us a little more details. So here we go. So a precipitation reaction, guys, like I said, it's something we've already talked about. It's simply a double replacement reaction that forms a solid, okay, when it reacts. So remember last time when we did double replacements, we said it's more likely to occur if at least one of the products forms a solid. So we call those precipitation reactions. Remember, a precipitate is simply just a solid that forms during the chemical reaction. You would actually get a little solid forming on the bottom of, if you were doing a beaker, in the bottom of the beaker. So this is nothing we haven't talked about before. These occur when we get two soluble ionic substances are mixed together and a precipitate forms. Remember, three things happen during a chemical reaction. Bonds are broken, atoms rearrange, and bonds are reformed. So when those atoms are rearranged and the bond reformed, sometimes they're going to come into a new formation that creates a precipitate or solid on the bottom, and that's what we're looking at in this video. So look at this one. If we take magnesium sulfate plus sodium carbonate, now remember the AQ, that means aqueous, it means dissolved in water. So we have magnesium sulfate dissolved in water plus sodium carbonate, and they're going to form magnesium carbonate, and that's going to be S, that's our solid or our precipitate forms, and then we're also going to form sodium sulfate in there. So AQ stands for aqueous, remember, which means that the solvent is water and the chemical solution is dissolved in here. So let's kind of visualize this, what's going on here. So here's our equation. Let's say we take some magnesium sulfate and some sodium carbonate. We combine them. What we're going to form here in the bottom, this is our precipitate. Well, what is that exactly? Well, if we look up here in our equation, we can see that it is magnesium carbonate. Great. But now, what's going on with this sodium sulfate? Well, what we see is it's not floating around in the water as sodium sulfate. It's actually broken apart, or what we call dissociates, or ionized, into its ions. So we have some sulfate ions floating around in there. We have some sodium, and they're floating around independently. It's no longer one compound, sodium sulfate. They're actually floating around as ions. That's why we put the aqueous, or dissolved in water. And so that's what's going on in the precipitate. Now remember when we said when we did reaction type, we said if no precipitate forms, it's likely we're going to call it no reaction. Well, that would be because we'd have all the ions floating around in here still, kind of all mixed together, and nothing would really change. Okay, so like we said, in most every case, when a solid containing ions dissolves in water, those ions separate. Okay, they move around independently, just like we saw in the previous one with the sodium and the sulfate reminding. Okay, and so when you get a solution, okay, of these compounds going together, the solution is not only going to change to precipitate, but also those ions that are floating around. We can write it something like this. Here's what we started with. And remember, we formed magnesium carbonate with a solid, and then we had the sodium and the sulfate ions just kind of floating around in there in the solution. A couple terms let's get re-familiar with. Remember, soluble. Soluble means something is dissolved in the solution. It breaks apart, and we use AQ to represent this. Okay, and as we said earlier, if all the products are soluble, ions stay dissolved in the solution and no reaction takes place. That's what we talked about when we did our reaction types. Okay, nothing really happens because they were dissolved to start with, and they end up dissolved and just floating around afterwards. Now, if something is insoluble, okay, insoluble means it's not soluble, which means it doesn't stay broken apart. In fact, it's going to form a precipitate. It forms a solid. Okay, and we use S to represent this. Okay, other terms you'll hear used are insoluble or slightly soluble. Basically, they mean the same thing. If something's slightly soluble, only a little bit of it breaks apart, so we consider it to be a precipitate, at least for our perspective. Okay, when we did our reaction types, we had the big solubility chart that we looked at. We had ions on this side, ions on this side. We came together and see what letter they gave us, right? The S's and the P's and the A's and everything to predict if the reaction was occur. Well, now what we're going to do, we're actually going to do a more simplified version of it, okay? And what we see is a salt that contains certain ions we're always going to be considerable. And these are the rules that we use for AP Chem, and so we're going to bring them on here. Now that you know how to use the solubility chart, I'm going to break it down, make it a little bit easier for you. So if a salt contains any of the following four ions in it, we're going to consider it to always be soluble. The first one is sodium. Okay. Second one is potassium, and then we have two polyatomics. We have ammonium, right? That's our only positive polyatomics, and then we have nitrate. Okay, so these four you need to memorize. These are what we're going to go by. Now, are there more rules than this? Yes, but for us, we're going to keep it to these simple four things. So if a compound that forms has one of these four ions associated with it, it's going to be soluble. If it doesn't have one of these four associated with it, then we're going to say it forms a precipitate. Just FYI, some more general rules. As we said, most nitrate salts are soluble, okay, meaning they break apart. Most alkali, which is group 1A salts, and ammonia are soluble. We already talked about that. Here's one we haven't talked about. Most chlorine, bromine, and iodine salts are soluble except when they mix with silver, lead, and mercury. Okay, most sulfate salts are soluble except for barium sulfate, lead 2 sulfate, mercury sulfate, and then calcium sulfate, which we saw earlier in our example there. Most hydroxide are only slightly soluble. Remember, slightly soluble, think forms a precipitate. Okay, and then we can also look at this one. Most sulfides, carbonates, chromates, and phosphates are slightly soluble. Remember, slightly soluble means a precipitate. So, like I said, this is just kind of FYI stuff. There are more complex rules than what we're going to go by, but we're going to go with those four compounds. If a salt contains those, then it's going to be soluble. Okay, try this one on your own. Pause it and then come back. All right, which of the following ions form compounds with lead-2 that are generally soluble in water? So if we look at our list, think about our four that we have to memorize. The only one that fits that list, right, are nitrates. Well, Mr. J, I thought you said sodium's on there. I did, but notice, sodium is a cation. Lead-2 is a cation, right? Opposites attract, so we're not going to have two cations making a compound. That's why sodium is not included in this one. Little trick question there. All right, so let's talk about ways that we can write equations for this. Now that we know what's actually going on in these precipitation reactions, we can get a little more detail. And there's three ways that we can write them. The first one is the molecular equation. That's what we've been doing so far. That's nothing new. And then the other two are our new ones. We have the complete ionic and the net ionic equation. Both of these give us a little more information about what's going on in chemical reactions. So let's go ahead and look at all three of these really quick. The molecular equation, also sometimes known as a formula equation. Molecular equation is a little misnomer, right? Because we know that ionic compounds are salts, not molecules, but it takes the name molecular equation anyways, okay? So in the molecular equation, you give the overall reaction stoichiometry, right, coefficients, but not necessarily the actual forms that the reactants and products are in a solution, okay? We show everything put together. We don't show it broken apart, okay? So the reactants and products are usually shown as compounds, not as aqueous ions, okay? So here's an example. Silver nitrate combines with sodium chloride, okay? So we use our solubility rule. So let's see, who's going to form? We would form silver chloride, okay? Neither of those are on our soluble, so that's going to form precipitate. And then we form sodium nitrate. Both of those are on our soluble list. So our precipitate is going to be silver chloride, and sodium nitrate is going to be an aqueous solution. So we should get an equation that looks something like this. Excuse me. This is what we have been doing since we learned how to write these equations. Nothing new. Now, here's the new part. Complete ionic equations. These are going to give us a little bit more information about what's actually going on in an equation. So in these equations, it shows how the species in the reaction dissociate or broken apart when they're in the water. Okay, it represents the reactants and products that are strong electrolytes. Remember, Electrolytes, we talked about earlier, are substances that can conduct electricity. Why can they conduct electricity? Because they have ions, or forms ions. We need the ions to do it, okay? And so if we take the one we just did, okay, if we write this out in complete ionic form, anybody or any species that is aqueous, we're going to break apart and show it in the ion form. So silver nitrate is going to break down to silver plus NO3 aqueous, and then we have sodium plus and Cl aqueous. Yes, you need the charges, okay? And then on the other side, anything that's a solid is going to stay a solid. Okay, so silver chloride stays a solid, but then sodium and nitrate breaks apart. Just a little note here, guys. Let's say, for example, if we had Ag2NO3, it's not correct, but let's say that. What we would do in that case, your 2 subscript here becomes a coefficient, so it would be 2AgNO3. If the whole thing was in parentheses, or if we had a 2 in front of here, we'd have 2 Ags plus 2 NO3s. Okay, so make sure you're carrying the subscripts to the front of the element that's with it, and coefficients go to everything in the equation. All right, let's go to the third type here. The third type is what we call the net ionic. And a net ionic includes only the solutions of compound that actually change. So if they're the same if they look the same on the product side and the reactant side of a complete ionic, then we can get rid of them. Okay, so it's only showing the components that actually, the species that actually react. Those that don't react, we call spectator ions. Think about spectators in a sporting event, right? They sit on the side, they don't affect the game at all. We can, kind of get rid of them and we'd still have the game going on. Well, that's what spectators in a net ionic equation are like. They don't affect it, so we can get rid of them. Okay, so spectator ions, we can define it as ions that are present in the solution both before and after the reaction. Since they don't change, we take them out. Okay, they're not included in net ionic. So if we take our complete ionic that we do, we start looking for things that are the same on both reactants products. So first one, we can see there's nitrate, we get rid of that, and then we see sodium. Okay, since they're the same on both sides, we can get rid of them, and then to write the net ionic equation, it just includes what's left, what actually changes. So what do we have? We have sodium aqueous plus chlorine aqueous to give us silver chloride. So that's our net ionic equation. So molecular shows us everything, okay, but it shows the compounds written, or the species written as compounds. Complete ionic shows everything as aqueous broken apart, solids stay together, and then net ionic only shows us what's changing. Okay, in this example, the sodium and nitrate are spectator ions, so we got rid of them. All right, guys, let's go ahead and try this example here. It says, write the correct formula equation, also known as molecular equation, complete ionic and net ionic for the reaction between cobalt-2 chloride and sodium hydroxide. So let's see. If these two react, who's going to form? Well, cobalt is going to go with hydroxide. Okay, neither of those are on our soluble list, so that's going to form precipitate. And then we have sodium and chloride. Well, sodium's on our soluble list, so we know that's going to be aqueous. So our molecular formula should look something like this. Now notice I went ahead and balanced it. Okay, so that's really important. All right, so now what's going on? For the complete ionic, anybody that has an aqueous here, we're going to break apart. So cobalt-2 chloride is going to break apart, sodium hydroxide. Cobalt-2 hydroxide is not because it's solid, and then sodium chloride. Now, here's what I was talking about earlier. This too is going to apply to both sodium hydroxide, same over here, 2 sodiums and 2 chlorides. So when we write our complete ionic, it's going to look something like this. We get cobalt. Now here's our 2 for chloride, 2 chloride minuses. Okay, now it only goes to chloride because it's a subscript. In the second case here, our 2 here is a coefficient, so it goes to both compounds. So it's 2 sodiums plus 2 hydroxide. All right, and then for products, we're going to keep our cobalt-2 hydroxide together, but then the sodium chloride, it's aqueous, going to break apart, but the 2 goes back to both sodium and chlorine. Don't forget the charges. All right, and then find the net ionic equation. We have to look and see who's the same on both sides, and we can get rid of them. The way I usually look at this is I figured out who formed, what's different, what changed, and what caused those, and that's what I'm going to end up keeping. Okay, so what we see, I'm going to have cobalt plus 2 hydroxide to give me cobalt 2 hydroxide. And there is our net ionic equation. So not too bad. All right, let me have you try this one on your own. As soon as I show it to you, pause it, do the same thing we just did, and then come back. So it says, complete and balance the following reactions. Determine in each case if a precipitate is formed. If the precipitate is formed, write the net ionic. Okay? You don't necessarily have to write the complete ionic, but you have to write the net ionic. So here's our 4 reactions. Go ahead, pause this, and come back once you're done. All right, hopefully you didn't cheat because it's not going to do you any good. All right, let's look at A here. So in A, what we get is there is our reaction. We see this has NO3, so it's going to be aqueous. Here is PbCl2, that's our solid. Okay, so now we need to write our net ionic. Well, I know I'm going to form PbCl2, so that's going to be my solid. Where'd that come from? Well, I got 1 Pb plus 2 here plus 2 Cl minuses. Okay, so there's my net ionic. So I'm kind of working backwards from my precipitate to figure that. Okay, in B here, once again, we're forming a solid in silver bromide. So to write my net ionic, I work backwards. I got 2 silvers, because I got 2 there, plus 2 bromines to give me 2 AgBr2. How about letter C here? In this case, we're going to form calcium chloride and then iron hydroxide. Okay, what we see in this case, now this is a weird one. This doesn't fall under our always soluble list. It does happen to be soluble. It's one of those exceptions that we talked about. But if you put precipitate for this, that's fine as well. But technically, if we go back to look at our solubility table, this is the only one that forms. What we see is a lot of times, in most cases, the chlorines will be soluble, but not all. Okay. So here we go. So if we're forming a FeOH2, iron 3 hydroxide, right? We need 2 irons from here, and then we have 2 hydroxide times the 3 here, so 6 hydroxide to give us 2 FeO. And here we have sodium hydroxide combined with hydrochloric acid to give us sodium chloride and HOH. Now, did anything change? Yeah. What we saw is sodium and chlorine are going to stay the same. We formed HOH, also known as water H2O. Just have it written a little bit different here. So this is a change. So we are still going to show the net ionic for this. So what do we need? Well, we have hydroxide from here plus H from here to give us HOH. So there is our net ionic equation for that one. Okay, we have rather than a solid, we have a liquid, but this is something new that got formed. So we are going to write the net ionic for that. All right, guys. So today we talked about precipitation reactions, which are just simply a double replacement reaction that forms a precipitate. Okay, we talked about our new rules for it. We said if anything contains sodium, potassium, nitrate, and ammonium, they're always going to be soluble. Otherwise, we'll assume that the product being formed is will form a precipitate. Now, granted, that's a very simplified one. We saw some examples in the last one where that's not always the case, but for us, we're going to go with that. Then we also learned the difference between a molecular, complete ionic, and net ionic equations are. We learned how to write the complete ionic and net ionic. You guys, if you have any questions, please drop me an email. Otherwise, I will talk to you later. Take care.